This is section 3.5, where we left off, and we had talked already about horizontal shifts and vertical shifts. Now we're going to talk about vertical stretches and compressions. So we have these three graphs. Again, we can plot points. Whoops. So we have x squared, 2x squared, and 1/2 x squared. So let's do our standard -2, -1, 0, 1, and 2 for x. And let's see. For x squared, if we put -2 in, we have 4. -1 gives us 1, 0, 1, and 4. Okay, for 2x squared, we just take x squared and multiply it by 2. So we get 8, 2, 0, 2, 8. And then for 1/2 x squared, we take x squared and divide it by 2. So we get 2, 1/2, 0, 1/2, and 2. So let's plot all those and see what happens. So our basic x squared, whoops, when we plot the points, looks like this. Okay, with 2x squared, instead of a 4, we've doubled the value. Same thing for the 1, and same thing on the right-hand side. So we still get a parabola, but it's narrower. And for 1/2 x squared, the y values are shorter, so the parabola looks wider. So what does that tell us about the rules for vertical stretching and compressing? Well, it tells us this. If we take our basic function and multiply it by a number that is a positive number, if that number is bigger than 1, then the graph of the original function is stretched by a factor of a units. If the number we're multiplying by is between 0 and 1, so between 0 and 1, meaning a proper fraction, then the graph is what we call compressed. Vertically by a factor of a units. So the key here is whether the number we're multiplying by is bigger than 1 or between 0 and 1. Okay, now that's the vertical stretches and compressions. Let's talk for a minute about horizontal stretches and compressions. So we can again make a table of values here. We have x, absolute value of x, 1/2 absolute value of x. Sorry, I wrote that wrong. The absolute value of 1/2 x and the absolute value of 2x. So hopefully you notice that the difference between this and the vertical stretches and compressions is this time the things we're multiplying are inside the parent function. Meaning if this is our parent function, the absolute value of x, then the multiplication part is inside the absolute value. So let's do -4, -2, 0, 2, and 4. And the only reason I'm doing that is to make the arithmetic look a little bit better. So the absolute value of -4 is 4. -2's absolute value is 2. And then continuing on, we get 0, 2, and 4. Okay, if we plug in -4 to 1/2 x, the absolute value of 1/2 x, we get 1/2 times -4, which is -2. And then when we take the absolute value of that, it becomes positive. So let's see, we get 1, 0, 1, and 2 if we fill out that line. And for the absolute value of 2x, we get 8, 4, 0, 4, and 8. So let's start with the absolute value of x. We get this nice V shape. If I can get the points in the right spot. So this one's the absolute value of x. Now let's do half the absolute value of x. So at -4, we get 2. At -2, we get 1. And then 0, 1, 2. So here's the absolute value of 1/2 x. And for 2x, it's going to get steeper. So we have -4, 8, 2, 4. So when we graph the absolute value of 2x, it gets steeper. So this one's the absolute value of 2x. Okay, so let's go formalize the rules of this one. For this one, summarizing our horizontal stretches and compressions, if we do the multiplication inside the function, then the graph of the original function, if that number we're multiplying by is greater than 1, that is a compression horizontally. So we say it's compressed horizontally by a factor of 1/a. If the A is multiplied, that we're multiplying by, is a proper fraction. Remember, this time it's a proper fraction, so between 0 and 1, then we're stretched horizontally by a factor of 1 over A units. So let's go look at Desmos for a minute. How can we tell the difference between a vertical and a horizontal shift if all we have is the graph? So right now, all that's on this graph is plain old x squared. So as you can see, right here is the point -1, 1. Over here is the point 1, 1. So let's add the 2x squared, the one that is a vertical stretch. How do we know that's a vertical stretch? Well, if we look at an x value of 1, our parent function, x squared, should have a y of 1. Here, if we look at -1, our function has a value of 2. So for the same input, the -1, the y value got bigger. That's how we know that that is a vertical stretch. Now, what if we were to put a horizontal compression? That is the 2 on the inside, so we have the quantity 2x squared. Well, this one, if we look at our 1, 1 value, our -1, +1, we can see that the y value is 4 times that. That's not really a good way to look, though, because then we might think at the point 2, 4 that our y value might be 16, which actually would be true. But what really is happening here is that the -1, 1, to get a value of 1, we have to put in an x value that is half of that. So -1/2. So that makes it a horizontal compression. I know it's a little difficult to tell, and normally I don't think we're going to do that to you. It's mostly, can you go from the equation to the graph? I just wanted to point that out, though. All right, that's all for this part. I will continue with section 3.5 in the next video.